Great, thanks. I'll share my screen as well. Yeah, you can see my screen as well right now. Is the screen visible? Sorry.
Yes.
Okay, great, thanks. Okay, so let's start. This is like Yashasvi said, this is like session number 2. And let me introduce myself. My name is Vijayalaxmi Cigala. So I have an experience of 9 years in IT. And I work in capacity of a backend engineer, basically in JVM based technologies. And currently based hopefully I put in some sweat in this and do justice to this. Okay. Next. So this is the agenda for the session. So it's like introduction to data structures, time complexities, then their applications, practice problems, quiz. But then this is not the exact sequence that we might go in because it's quite helpful if we talk about data structures, their applications together. So they are intertwined. Right. Okay, so before talking about data structure, I would like to share one experience. So usually at the kind of experience that I have, or even at lesser experiences, I was often asked about, designing systems or, given problems to solve, wherein I had to, like, of course, provide solution. And trust me, like starting off your answer with data structures really helps a lot because when it's a big problem, it's a black box for you. Taking chunk by chunk, and that chunk, like initial chunk as data structure, really helps you design a better solution. And yeah, and like interview questions never do come in the form of like tell me data structures like linked list or arrays or stacks, but their applications. So hopefully like by the end of the session I am able to do justice and help you out with answering those kind of questions. Yeah, with this let's begin. What's data structure? Like the title says, it's data plus structure. And why do we need them? It's just a way of organizing data, like for better visualization and for better access. Better visualization actually leads to better design. So it's like the real representation of the data with what your problem is. That really helps in designing better solutions. And better access, by means of better access, I mean to say well performant solution also. So it's a better, it's a good combo if you have a good design as well as well performant solution. So that's why we need data structures. And to keep it interactive, if you guys have any questions or anything, you can just put it on chat. If I'm not able to like address it quickly, like because I am presenting, just let me know, or you can just unmute yourself and like we can just discuss. Yeah. Okay, so the data structures that we would be talking of today would be arrays, linked lists, stacks, queues, trees, and graphs. And their types basically. So these are the ADTs, abstract data types, if you remember from the college lessons. Yeah, let's move on to arrays first. Yeah, arrays, the definition, as the slide says, it's a linear data structure having elements of same type stored at contiguous locations. So the word contiguous locations is very important in case of arrays. And that is important because the random access is quite efficient in arrays, and it's efficient because of the contiguous locations. So Yeah, you can see my whole slide, right? It's not anything else on the screen that you guys see, right?
Yep, it's nice and clear, Vijayalaxmi.
Sure, thanks, Kate. Okay, so like I have a like good picture of this. So this is an array with contiguous locations. So the data elements are 11, 9, 17, 89, etc. And these are the indexes in the array at which they are stored. Um, so there are types of arrays as well. Like there's a static array as well as a dynamic array. So to talk about a static array is something that somebody has asked a question. Is it? Okay, Anup, let me just finish this point and I'll answer your question. Okay, so a static array is something where you predefine or predetermine the number of allocations that you see for your array. So say in some case I see my list, my array being of size 10, and I allocate it. So that can be a static one. A dynamic is something that where I do not foresee uh, the size, and I keep on adding, and then at some point of time there's an overflow, and all my elements move to a different location. So it's a array copy to that location and then insertion. So these are the differences for static and dynamic arrays. Application, as you see, is like a good ideal situation would be like you have to transfer some fixed number of elements from one place to another. So in this case, the good thing is you already know the size of elements that you foresee to be transferred. So this is ideal situation for usage of arrays. Yeah. So coming to the question that Anup just asked, arrays in JavaScript can store types of data as well. Okay. 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 So that's a language. What you say, benefit, right? I mean, this is also possible in Groovy, where you can just store different types of objects in a list, and I don't give any type. So this is quite possible, but from the ADT perspective, it's said similar type, because you don't have to typecast, or when you're iterating, or when you're actually getting the elements, you don't have to really bother what kind it is. So that's the benefit of having a same type. Okay, let me move on to the next one. Sorry. Yeah, linked list. A linked list is, again, as the definition says, a dynamic linear data structure consisting of connected nodes comprising of data and reference to next node. So you remember, like I talked about, array having a problem where you have to foresee the size of your array, and dynamism actually comes at a cost, which is like your array gets copied to a new location, and then the insertion really happens. So in order to kind of cater such situations, linked list is a good savior, I would say. So as the definition says, it's a link between the nodes, and each node is having data packet, and also a reference to the next node. So that's how a linked list is formed. So we do have a lot of types of linked list, frankly speaking, based on the primitives like singly, doubly, circular. So, you can just see a composite, which is doubly circular, which is listed here. Right. So what we can do is let's go one by one, each of the types. I do have like animations for some of them. I do not have some like animations for some of the others, and hopefully I try to explain them. Yeah, let's go to singly. Yeah, right. So we can see like pre-built singly linked list. You can see there's a head. There's a head node which is pointing to the next node. That next node has data. Of course, head also has data, and a reference to the next one. Then the next node also has data and reference to the next one. So the size of this is 7 currently, and the end node, which is 89, is pointing to null. If you remember the diagram, which is the ending one. So the operations allowed on a singly linked list are like, you can just add at any location, remove from any location. You can search. That's basically it. So let's say we want to do a search. It will do a search. So 6. So that's how it is searched. So it starts from head, then like checks whether that element matches. No. Goes to next, matches. No. And that's how it stops at the location where it actually matches. So if we do a search for an element which does not exist, so actually it will like traverse through the whole the list, and we'll say it's not found, right? So yeah. So the reason we are seeing these animations are like because we are going to talk about time complexities, and these animations will help you through the time complexities part. The other operations like we talked is like insert. So now like insert 85 on the head. So it gets inserted, and then 85 is your new head, and then 22 is the next node. And likewise, there's a remove. Say on a remove. Yeah, that's so I removed a head. But I can remove by index. Yeah. So the reason it is keeping a rack of pre and temp is because it wants to remember where it wants to point after the deletion. Yeah. So that's mostly about it. You can so insertion and deletion, to be clear, is not just on the head or tail. It can happen anywhere in between. Just that the nodes get rearranged afterwards. That's all about Syncly. Any questions or anything? Just nudge me. Yeah. Okay. So this was all about Syncly, single reference. So there's one drawback that we are gonna talk about, which actually led to doubly, and that's you can just keep on moving forward, but then you cannot like move backwards. So like if at any point of time you want to like really like you're at 43 and go back to say 2 because your problem statement says so, you'll have to like end this and then again go to head and then start off. So like to solve that problem, we have a doubly linked list. So this is the DLL. So if you see, the direction of the arrows is both. So now our node is not just data and next node, it's also previous node. That's how our node looks like in a linked list. So similar kind of operations are offered here. You just add an element 5. Sorry, what did I do? Oh, I did a search and that element did not exist. 17 does exist, so it will find it. Yeah, right. So if I do an insert, I can do an insert on, okay, let me do it. Okay, so I've inserted on the end part, 80, yeah. And then if I wanna remove, I just removed the head, and and again, to be clear, deletions and insertions can happen at any point of time. That's the beauty of linked lists as against the arrays. And doubly just offers a backward reference to the nodes. So at any point of time 17 gets removed, now 31 will point to 80 and 80 will point to 31. So that's the mutual locking that they will have to keep. Sure. Yeah, Anup, I just read your question. I do have it in slides. So I do have the applications listed here. So the way I'm going to cover is like talk about definition types and then their applications. So doubly, as you can see, you just have playlist with shuffle mode, without shuffle mode. So basically, if you wanna, visualize this, so I have a playlist of 3 songs, and when I start off playing this, I can move to next. 17, and then like I happen to like 31 again, so I can just move back and forth. Yeah, this is example of DLL. Right. So again, there's one problem here, which we will talk about in circular. Right. So that the problem is that now head and tail are actually not attached. So circular just make sure the tail and head are like reference to each other. That's what it is. So we'll see an animation for this as well. Okay, so this is a different site. Sorry, I couldn't find a circular linked list on the same site. So what I'll do is I'll start inserting. So the point of interest should be this. The code is just randomly generated. So if you insert 50, and now so now the last is pointing to 50, and 50 is again pointing to 50 because it's just a single node. Now say I insert 45 in the front. So now my head would be 45. Yeah, 45 points to 50 and 50 again points to 45. That's how, that's a cycle that completes. Likewise to make it better. So I'll insert 78 in the back. So now my 78 points to 45, right? And my last node becomes 78. And again, just because this UI does not offer me to insert in between, I would have shown you otherwise. But this, this node can be placed anywhere. It's just that, your tail points to the head. That's how your circular linked list is. And based off this, you can make composites, you can make doubly circular and all. So like what doubly circular would do is, so this, again, if you look at the arrow direction, so this is singly circular list. Circular list is by default singly, but if it's if there's a need to have a backward reference, then you can make it a doubly circular linked list. That's how the composites to come. So like your 50 will point to 45, 78 will point to 50. Yeah, and 45 will again point to 70. That's all. Yeah. So coming to the applications, so a singly is like, so usually singlies are like not so much used because you often need the, there would be a use case where you would want to, reference the backward node, as well as the front node. So doubly has a lot of use cases. Singly has very less. But if you know reading streams, or if you are like working on Kafka partitions, then this is something that you can relate very well. You have streams of data. You start reading one by one. There is no going back. It's just going ahead. And if, especially in case of Kafka partitions, you can just go by offsets. You can just do a random access by offsets and all. So that's one of the use case for singly. Doubly, like I just told, playlist without shuffle mode. So you have sequential songs, and then you can do backward as well as front, like forward it or go back. That's how. And then doubly circular is like playlist without shuffle, and just that your after your end song, your first song will be played. That's how you can visualize your doubly circular as. So I'll wait here. Do we have any questions or anything before we move on to the next section?
There are questions, Vijay.
Oh, okay. Sorry. I answered one for Anu. Will search use for detections in a DLL? Okay, as compared to in a singly linked list where we are forced to go sequentially current pointer onwards. Yeah, DLL you can like go backwards and forward. It's just that whenever you start searching in a linked list, be it any type, you started from the head. So when you start off with the head, and then at any point of time, let me just open up the DLL thing to make it simple. So, yeah, so you would always like start off with the head to search an element. But then, when you are at 17 and then you decide, you have a situation wherein you want to go back, you can just go back. But then, yeah, you always know your search did not succeed at this point when you like started moving forwards. But yeah, that's possible. You can do backward, like reverse search. Right. Okay. Does that answer your question, Gabe? Sorry, I am having some problems with my Zoom. You guys able to see my screen, right?
No, Vijayalaxmi. It's screen sharing.
Oh, okay. Okay. I guessed it. It's not working. Right. So when I was like talking about the DLL thing, did you like see my screen? Like, was it visible then?
Yeah, now it's good. Thank you.
Oh, sorry. So to answer your question again, I was saying, whenever you start like searching, you often like you usually start off with a head. So you start with the head and then go to the next node and then to the next node until you actually do an exhaustive search. But then with the benefits of DLL, of course, you can go back for a reverse search, but then you have already traversed it and it was not a match, so you might not want to go back. But then that's possible. That's what I was trying to say. Okay. So I'll move on to the next part. Yeah. So we do have a stack. So stack is like by definition a container of objects that are inserted and removed in LIFO principle. So sorry, apologies. It was okay. Yeah, it was. So I was talking about this. So LIFO is like last in first out. So as you can see in the diagram, you just keep on adding the elements here. The sequence of elements that go in is the sequence they like keep on piling up, and the latest one will be the one that will be always pulled, from a stack. So push, pop, peek are the operations. Peek is nothing but uh, so so this when you keep on pushing, there's a reference called top, which keeps on pointing to your latest element. So in this case, it's 1. So your top will point to 1. Next will be 2. Likewise, as the insertion goes on. And when you do a peek on that, peek is never gonna remove an element. Sorry. Sorry. Okay. So your peek would actually not remove an element. It will just give you a peek of what top element is. And when you like doing pop, it actually pops out the latest element from the stack, and the top gets realigned to the latest. So in this case, when I do a pop, now my top is 4. I just get the element 5. Likewise, this as the diagram shows. I do have a small demo as well for this. Right. So this is the stack. Like we were talking about the head. So the representation here is like a linked list, but ideally we don't need a tail or anything. In stack, it's always a top pointer. So here, if you want to look at as, so the sequence of element insertion was 37, 34, 54, 32, 87, 42, and 45. So that makes 45 my latest element, and my top is like pointing to 45. Now, if I want to do just a peek, it will not remove the element, but it will just give me a peek of, okay, this was even better. If I want to do a peek, it should give me the number 75. I'm not sure if it's working or not. If I want to do pop, so this will be popped out, and then my latest top becomes 2. Likewise, if I want to push after that, I push 53. So, my top will be now 53. So that's how it is. So like interestingly, stack is a very trivial data structure, but then it kind of solves a lot of problems, um, which we kind of happen to solve in day-to-day basis. One of them being recursion. You do have problems where recursion is the solution, like your stack trace or function calls. So that's one of the typical scenarios where stacks do come handy. Other than that, one of the problems I was thinking is uh, say if I am not able to push out notifications or you know or state of objects to my clients, and I like for some reason and I keep them piling up like this. So at any point of time when my connection through to the client starts, then I can always push out the latest ones and just neglect the intermediate uh, updates on the objects. That's one of the solutions to kind of avoiding sending all the updates, but just the latest one. I do have some questions on chat, I suppose. Right. Okay. So Anup is saying recursion can be used with any data structure, right? Well, uh, not really. I mean, you might able to solve with hacks, but then the beauty of what Stack offers is something that you can solve it with recursion. Of course, you can do, in place, what do you say, another alternative to use a tree or something. Um, you're not doing recursion, but then you're doing alternate of recursion. But yeah. Right. Okay. If that answers the question, I'll just move on to the next. Right. So the next thing on our plate is queue. So queue by definition is okay. Queue by definition is a container of objects that are inserted and removed according to FIFO principle. So it's the day-to-day activity that we do. We form a queue, and then the person who was really the first in the queue gets addressed. That's the principle used in queue, first in, first out. But then that's not really something that also adheres to all sorts of queues. Like if you're on a talk of DQ, it's not really doing first in, first out. It's actually first in, first out plus last also. So yeah, we can talk through that in the demos. But it's again like a linear data structure wherein you are just storing data, and it's just that the sequence matters for you, and sequence of getting the objects matters to you. That's how it is. So let's talk about a simple queue. Right. So we do have a queue here, which is with these elements, and yeah, so the operations offered are peak, NQ, DQ. Like NQ is adding to the queue, and addition in a simple queue happens at the rear, and DQ is like removing from the queue, which happens from the front. So that's how NQ in the end and DQ in the start. Okay, so let's see what does NQ do now. I want to do 57 at 57. So now my array would be 57. So now my 19 is like next, like pointing to 57. So that like defines the sequence order of the elements here. DQ, when I do DQ, the first element would be like taken off, and now the next element becomes my front. Likewise, one more. Yeah, so you can see the sequences being adhered And if you want to do peak, peak is just going to give you the number, but not really do a DQ. That's a simple queue. Let's talk about DQ. Yeah. So this is DQ. Yeah. So one more thing, not to confuse this DQ with this DQ. So DQ, like Q, a proper DQ is operation to like remove element from the front, and this DQ with like one set less of UE is a double-ended queue, right? So now we can see double-ended queue. The problem that we had in queue was like, it's not really a problem, frankly speaking. If you want to like, respect the sequence, then queue is the best. But, there are like some cases wherein you would want to have, insertion and deletions at both the ends, rather than shifting elements, so that's where DQ comes handy. So you can actually, so this is my front, this is my rear. I can actually add in the front or in the back by actually not shifting elements or doing anything. So if I want to do add at the front, which was not possible in a normal queue, I can do just this. So this becomes my front and this is still my rear. Likewise, DQ is like now I can even remove from back. Yeah. So that's how it is. So just just to just to keep it like, something which you can visualize is, you just think of, a counter. Say you have a counter here and you have like 3 people piled up here for some service, and for some reason now a counter here starts, and you can start servicing 15 from here, and 57 is getting serviced from here. Ideally it's not fair, but then yeah, that's one of those use cases that is really handy to think through DQ. Okay, so we have next one on plate is a circular queue. A circular queue is nothing but, ideally queue is a dynamic data structure. So basically it's uh, never at the static time that you have to think of how many nodes you're going to have, or like that. But when it is implemented by an array, which constrains you to have elements defined, like number of elements defined at the compile time, that time circular queue does come handy. And how does it come handy? We'll see this. Okay, so say these are like my array elements. Let me like remove some of them to like explain them in a better way, right? Okay, so now I have 5 elements, and like basically my array was initialized with 5 elements here. So when I kind of remove one element, so ideally these elements keep coming here, right? These keep coming here. So say if I just to optimize the operation, I don't make my array shift at all. I just keep this mark this as like null or something like that, and just keep adding here. But like ideally, if I have removed 95, this location is vacant, and ideally the size is 5, and I have 4 elements, and I can add one more element, but array won't allow me to do that because I have kept this reserved. This is like gone. This is a hole. So in such cases, circular linked list do comes handy. So basically what happens is, like in such a situation, if there's one more element that's going to be added, that will be added here, but my tail would still be that, and head would be still 20. That's how it is. So this is like a very, I would say, rare scenario where you don't use a circular one. And again, like not to forget, since it's normal queue, normal circular queue, insertions and deletions will just happen on their own ends. Like insertion will happen in the end, and deletion would happen from the front. Yeah. One of the other queues, which is like very widely used, as a priority queue. So a priority queue is another sort of queue where you're not really adhering to first in first out principle, but rather adhering to giving more priority to the elements which have higher priority. So the elements with higher priority will be the one which will be dequeued first. That's what the principle is. So I do have an example, like would be better for visualization. Right. Okay. So this talks about min heap. So this is a way of implementation. So ideally for this example, just look at this structure and know the tree that would be formed below. Okay. So now say I have element with 5, I inserted. Yeah. So that gets inserted in the front. Now I do have another element 7. So that gets inserted next. Just skip this. We are going to talk about this in trees. Yeah, just look at this. So 7 gets appended here. The next one is say 8. So it will go at the third one, right? And now say I have another element 1, which I'm going to insert. And this is min heap. That means the lesser the number, that gets more priority. So when I do insert, so it will get swapped with each of the elements and just surface to the top. So now you can see, ideally one was inserted like last, but then the first one to be dequeued would be 1. So that's where the priority is being respected. Right. So applications for this for these structures is for simple queue, your messaging queues are like the best examples for this. DQ is very, very niche. So I would say palindrome checker, where you'd wanna do first and end elements to be matched and removed, and then you go to the center. The more you go to the center, you know it's a palindrome or not. So that's one of the applications for DQ. Circular queue is again audio playlist without shuffle. You can just go in sequence like this, right? And priority queue is like you have this your priority based process handling, which is done in schedulers. So this is one of the schemes, but then there could be another schemes like there could be round robin or anything. This is one of them, like process with higher priority would be like executed first, and then the subsequent ones with the lower priority ones. So that's where priority queue would come handy. I'll quickly check the questions or what's going on the chat. Okay, how to differentiate an DQ and circular linked list? Okay, a DQ and a circular linked list. So in circular linked list, you still have the nature. You can actually go visit intermediate nodes, but then in DQ you can't, right? You have to really DQ, get the elements off, and then you can just compare or see what the element is. In circular linked list, you don't have to remove anything. You just keep traversing, which is fine. So random access is something that you can do in linked list, but in DQ you have to compulsorily just remove the elements. Unless you want to do peak, but then peak is again restricted to the front or rare. Manish, what are you trying to say? DQ visualization. I didn't get your question. Do you want to talk about your question better? DQ visualization, how is it used? Okay, so so we talked about palindrome checker. I'll take you to, sorry, I'll take you to how it is really used. Right. Okay. So when I said palindrome checker, what I'll do is I'll just insert one more element, or rather let me create an empty one. So I would enqueue 57 front, enqueue 96. Okay. Now I would enqueue in the back, which is, oh, sorry, I wanted to enqueue 57 in the end, and oh, okay. Oh, so there's this limitation of this visualization. But if you want to think of it as, you're having a string and you want to put it through a palindrome check. So the way you would want to do is a palindrome is like, um, your left side and right side should match. That's how a palindrome is, right? So ideal scenario would be SAAS is a palindrome, or SAS is also a palindrome. So if you take the example of SAS, this is SAS. So what you do is your head and tail would match SS. They are like removed from your DQ. Now the pointer goes to 57. It will check. It's just one vertex, and it's a palindrome. But now say if I had SAL. So in the very first stance, your head and tail would be like matched, try to be matched, but they don't match. So your palindrome check fails there itself. So that's how your DQ comes handy. Hopefully that explained your problem. Okay. Okay, so let's move on to the next part, which is a tree. So this is where we say bye to linear data structures, and we welcome nonlinear data structures. So we did talk about the applications, though, right? Yeah. Okay. So linear is like, you were traversing one way, and there was like literally no decision making or anything. But tree is data structure. Tree and graphs are data structures where, your the path that you take could be, there could be in numerous ways, and that's the reason they are non-linear data structures. So let's see what the definition of tree says. General tree is a tree where, case of a general tree. Um, so if you look at the diagram on the right side, so each of the circles that we see is a node, right? This is the root node. A is the root node. You have a point. Okay. So A is the root node. A is the root node, and B is a child. Likewise, C is a child of A. Okay. And B and C are siblings. So these are like a bit of terminologies that might help. And then this is the left subtree for A, and like this is C and G is a right subtree, and D, H, F, G are leaf nodes because they are the terminal nodes. They don't have any children below them. So that's leaf nodes. And like since we are here, like what a height of a tree is what, like when you start from the root to the farthest child, what is the number of edges that you come across. For example, in this tree, you can see if you want to traverse from A to H, you would want to go from A to B, B to E, and E to H. So basically, we have 3 nodes. The height of the tree makes it 3. So that's like a bit of theory about tree. And like a tree in general can have any number of children nodes and all. But then we have specialized like binary tree where you can have at the most 2 child nodes. It could be 0, 1, or 2. And like from that, we have binary search tree, ABL, and heap. So binary, we just spoke, it can have at the most 2 child nodes. So in this case, if you see B is having 3 child nodes, so this does not, stand for a binary tree. Had it been, you never had this F, B, like the subtree would have become a binary tree, and the whole tree would have become again a binary tree. Because, if you remove this F, every node is at the max having 2 child nodes. Like the leaf nodes have none, and E has 1, C also has 1. So that's what a binary tree is. We'll talk about the applications here. A specialized form of a binary tree is a binary search tree. Let's see what a binary search tree is. Like it still adheres to the principle of a binary tree, which is it has at the most 2 child nodes. But then binary search tree is ordered tree, and we'll talk about it why it is an ordered tree. Okay, so this is already a very complex tree. So let me just create a new one to start off with. Yeah, so we'll do this insertion. So I'm gonna do say 56. So that becomes my root node, right? So whatever gets inserted in the initial becomes the root node. Now, so I talked about ordering. So binary search tree is ordered in a way that every node, the left subtree would always be with the elements lesser than the node, and the right subtree would be all elements higher than the node. So let me make it clear. Like if I'm gonna make it 60, add 60, then 60 is not less than 56, so it should be added to the right side. Let's see. Right, there we go. Right. Likewise, I would insert say 64. So 64 is again like gonna go from 56 to 60, and then it's greater than 60, so it will be added to the right side of 60. So 17 would be like less than 56, so it's going to be attached to the left. And likewise, if I add 45, so it is less than 56, so it will go here, but it is greater than 17, so it will come here. So one thing to remember is like for given set of these numbers like 45, 17, 56, 60, and 64, the order of insertion is something that matters, because for the same number of elements, you would get end up in with a different binary search tree if the order of the elements of insertion were different, because your root node is something else now. So hopefully this makes sense. Yeah, everything to so the left subtree would be always lesser, like all the numbers to the left would be lesser than the node, not necessarily a root node, but then even this, or any node. The left subtree would always be lesser than the node, and the right subtree would be always the numbers with higher than the node. Right. Okay. Let's talk about avial tree. So an avial tree is a specialized version of binary search tree. So there was a problem which I forgot to tell you guys. Let me tell you now. And due to which we would need avial tree. So I'm gonna quickly create a new tree. So insert 23. So insert 32. Insert 39. Yeah. So now if you see, I have 3 elements. This is a binary tree because it respects the principle. But then if I want to do any operation like search, remove, or anything like that, then I would have to traverse through all the nodes starting from the root node. So basically, I would do a search on 23 that this does not match. So I'll move on to the next one, 32. It does not match, so I'll do another search at 39. So this does match. But if you see, this is skewed. This is this is offering me a linear search of order of O of n, which is not efficient. So that's the reason, and this is just 3-node tree, but then there could be like, very nasty trees which could be skewed, and then you just end up having linear time complexities for search. So in that case, an AVL tree is a very good savior, I would say. And let's see what an AVL tree is. So we do understand, right? This is a skewed tree, and a search operation would be very expensive on this. So a solution to this is, had it been balanced, and what is balanced, I'll tell you. So had it been balanced is, if your tree is not skewed in a direction, and your difference between the left subtree and right subtree is comparable, then that becomes balanced tree. And in this case, AVL tree has a principle of having at the max height difference of left and right subtree of 1. So that's what it keeps it as balanced, and we'll see the example here. Right. So we'll create a new one to like make it very clear. So I'm gonna add 45. We'll just do exactly what we did last time. So we'll do 67. And then I'm gonna do 89. So if you remember, in our binary search tree, it would append 89 here, like below 67, like to the right side. And then let's see what AVL tree does. It did add that. Yeah, okay. Now I'm gonna add one more, which is 99. Yeah. Right. Oh, I'm still doing binary search tree. I'm really sorry about that. So 54. Yeah. So the third insertion should kind of make it balance. Right? So it is checking, and it saw that it was skewed. The left subtree, like which was non-existent, with height 0, and the right subtree was with height 2. And AVL says, you can have a height difference of 1. So that's the reason it kind of rebalanced itself with rotation. So there are like types of rotations in AVL tree, but unfortunately that's out of scope of the current session. But then you do left rotation, you do right rotation, or you do a composite of those, and that's how you balance tree. So we'll add more and see. So this is now adding one more element. I'll add say 85 again. Right. So this is still not balancing because at the max one difference is allowed, which is still fine because there's no difference here. So I'll add 50, which will make it here, right? And another insert of 51. Yeah, so it rebalanced itself because it was going skewed here. So if I do 51, so this checks. Yeah, this is fine, no problems, because this is 1, 2, 3 height, this is 2, so this is still fine. And if I want to do 53 now, it should rebalance. It checks, rebalance. That's how it is. So it self-balances it, and the purpose of self-balancing is so that activity happens at the time of insertion itself, but then it gives you better searches. So when you do searches on this, it would be of order of O of log n, which is still better than a linear time complexity. Right. So this was about AVL. Let's talk about heap. Right. We just saw the screen during priority queue, and I like told you guys we're gonna talk about the tree. So this is where it is. So a heap is a complete binary tree. What do we mean by complete? As complete is something, and again it's binary tree. So this is not really an example of a binary tree, but then when a complete binary tree is when your your elements in the left side are at the maximum height, like how to explain that. So you can have vacant child nodes on your right, but then you keep on filling your left nodes like left to right, and each of them has up to 2 elements again as child nodes. Let's see as an example that will kind of make it clear. But then it's a complete binary tree. That's what it is. So if you do insertions, you do insert 77. Now, this is not the part you would want to look. This is the part you would want to look. So 88. Yeah. So this is the min heap. So 88 is less than 77. So that's fine. So the next element that I'm going to add is say 56. I'm purposefully adding this so that that goes to the right. Yeah. So I told you, right? The insertion always happens from left to right. Left to right, and then it balances, like swaps with the number to make the lowest number come to the top, because this is min heap. Had it been a max heap, the maximum number would be surfaced to the top, to the loop. So let's add a couple more and see what do I need. So when I insert 67, so 67 should get added here, right? But this is, yeah, so there was a comparison with the number 88, and there was a swap because 67 is less than 88. The next number that I'm going to add is, let me like reduce the animation speed so it's like clear. So I'm going to add 45. So when I'm going to add 45, this will get added here. Then there is a check with 67, they get swapped. And 67, 45 and 56 will be checked, and then they should get swapped. Let's see if it happens. So I'm going to insert. Yeah, right. And then this. So we in the end, we always like, in the end of the insertion, we always make sure the minimum number gets surfaced to the top. That's how it is. Hopefully this was helpful. Right. We'll talk about the applications. So first of all, trees in general are like when you want to like do decision making in general, because this, if you see the hierarchy, there are possibilities, like B has possibility of D, E, F. So it's one of the decision making data structures. So binary tree example would be a chatbot with Boolean answers. So often you guys go to websites where you're asked about questions, do you have this product or not? So you say yes or no. So if you say yes, based on that, the next question would be like fired to you. So you can just think of that as like question number 1, true, false. So true, then go to this. If it's false, then go to this. F is not there. Okay. So that's how binary tree can be represented as. Binary search tree. Like binary search tree is in general used for like sorting algorithms. But then there's like another one as well, like you can always get min-max numbers. So if you want to see a binary tree, binary search tree. Yeah, so I always get a number. The leftmost number is always the minimum one, and the rightmost one is my maximum one. So I can always determine what's my min and max from a binary search tree. An avial tree. So we saw access was faster in that case because it was like giving you better time complexity since it was not skewed and balanced. So it is like usually used in search intensive solutions. So there's another tree called as B tree. which is somewhat like avial tree, but then a bit different. So B trees, if you remember, like, you have database indexes based on B tree. So likewise, avial trees can be used in search intensive solutions, and they offer like search complexity of the same order, almost of the same order. And heap in general is like heap sort. And again, you can use a heap for implementing priority queues as well. That's what a tree is. Okay, so let me check the chat if there's any questions. Okay, so it's 20 for me, so I'm just going one by one. Okay. Computational expense.
Vijayalaxmi, I think Anup from, shall we take them back to front? So the animation, there were some confusion maybe over there, like the search happening from the left node for the search. I think he also had a question about the min heap. If you can, why did we bring in min heap? And was the point that it's a particular variation of the tree? If we could touch base on that again.
Yeah, like min heap and max heap are variants of heap in special, like in general. So what, like, just like priority queues, you define priority and then you keep on surfacing, elements with the higher priority. That's what heap does. You just keep on surfacing what you want. Like min heap is one of the variant of, a tree, and max heap is also one of the variants of tree, if that answers the question. And which animation actually were you confused about? Like which one?
So I think Anup mentioned it when we were demonstrating the min heap animation, where he mentioned it was not clear. So
okay, let me just read the question then. Like, that will better. That will be better for me to demonstrate. Even for insert, one has to first check for root node values and then check for its children. Yeah, insertion is definitely expensive in this case, but then your search becomes very effective as well. And when you have a predetermined policy in your head that priority of these elements should be like catered first, like that's when min heap comes really handy. So if you look at this, I'll just quickly make a small tree out of this. So there's no swap there. 7, right? Yeah, and like, sorry, but then this is not something to do with Java heap as well. If it's confusing you guys, but this is about like pure ADT, that like heap I was talking about. If that's one of the confusions as well. Yeah. So when I add 8, it's just retaining that. So yeah. So there's a like expense of swapping elements and surfacing the element to the top. But then when you start searching elements with higher priority or anything, then you are going to encounter them in the initial searches itself. So say you're going to do a search of 1, you just it's in the first attempt that you encounter it. And likewise, 3 and 7 are, say, with higher priorities. So the more you go to the depth is the expense that you have to pay when you are doing search. But here we have like sorted out elements with higher priority up, so the search is better, if that answers the question. Okay. Okay. I think Anup is fine. Manish is talking about something. So Manish is saying heap and stack looks similar. Not really, Manish. So in heap, we are like, paying attention to the priority or, the criteria that, the elements important to me, I am keeping them up, always like reordering and keeping them up. But in stack, it's like the order in which I accumulated them is the inverse of which I'm going to get them back. So I keep on adding, say, 138 in my stack. So the first one that I would get is 8 and not, these. So that's the difference between stack and heap. Yeah. Okay. So let's move on to the next one. So trees are in general interesting. Linear is very simple, but then decision making, those kind of scenarios, trees are very handy. Okay. Let's move on to the next one, which is graph. So graph is again, a decision making data structure, and it's not linear, and it has a lot of use cases that we use in our daily life. So this is going to be a bit interesting. What the definition is, a graph is a data structure consisting of a set of vertices. So these are the vertices, the circles that we see. So these are the vertices or nodes, and a set of edges or arcs connecting the vertices. So A and E is connected by an edge. So this is an edge. And we can define graph as, G of V. So basically vertices plus nodes. So that's what a graph says. Now we do have different types of graphs here. And this is not an exhaustive list. There's like n number of types of graphs typically, but we'll cover these. So what is an undirected, directed, and a weighted graph. So as you can see, there's a undirected graph. So like to make it clear, so far we were talking about data structures in terms of insertions and then searching them and then making some decisions on based of that. But then this is a data structure where you already have a set of nodes and you want to solve a problem. So this is not really where you delete, add, or something like do a search or something like that. But this is something which helps in decision making and solving other problems. And why am I saying that? We'll see in applications. So the ADT in general for graph would never say search or add, or you can of course add vertices to the graph and all, but that's not time complexities of that are not at all counted, because this is like undeterministic model. Okay, so what is undirected graph? So this one, first one is undirected graph. So you can see vertices are connected to each other. So when you are on A, you can go to E. From E, you can go back to A. E, you can go back to C, or E to D. So based on the edge that it has, it can go to any direction. So that's why it is called undirected graph. We'll talk about the applications here. And directed graph, the second one, is where you actually have the edges which are directed. So what does this mean is A to E is unidirectional, and E to A is not possible because the direction is not provided. So now the leisure of this goes away here. So it's strictly A to E, E to C, C to, sorry. Then at C, you don't have anything. So your traversal ends there itself. Yeah, so that's what a directed graph is. And weighted graph is like, you do traversal with, of course, a cost that you pay. So basically A to A is 1. Likewise, E to A, if it is undirected, which in this case it is, so it is 1. So like backwards and forwards is possible. So you must have solved some riddles, you start from one place to and end to a different place, and you would want to determine the shortest number of points, or shortest number of kilometers spent to reach from one point to another. So this is where your weighted graph comes into picture. So this is like a childhood riddle that we used to solve. So that's mostly about it. And self loop is like cyclic. Self loop is A points to itself, so you can like keep on going to A to itself. So had it been A and E, with so self loop is in general in context of cycles. So there could be cycles in graphs. So like A, E, D, B, A. So this forms a cycle in general. So that's what it talks about here. So if we talk about the applications, unfortunately, I did not find any animations for this, but then hopefully this diagram did help you guys. So directed in general is like packet flow in a network. So directed, like say, when you do trace route, when you now find out, where all your message packet is going through in a network. So that's how you can depict it. Like this is my my laptop, and then this goes to a gateway, then this goes to a terminal node or terminal DNS, and then like there's a hop, and then so that's like directed flow of packet. Undirected connections. Sorry, undirected is like connections. So like I do have a connection as Yashasvi. Say I have a connection as Gail. So of course that makes Gail and Yashasvi as my connections back. So that's like one of the way you could like see it as undirected. And directed and weighted. So this is an interesting one. Almost everybody uses Swiggy, Zomato, and all. So we do get suggestions for food. You can order this, of course, with a recommendation of the choice that we have. But then also keeping in mind the distance where we are, where the restaurant is, and how much the food preparation time takes. So this is where directed and weighted comes into picture. So say I am, okay, I don't have an example of directed and weighted here, but then just consider I am E. A is a restaurant, C is a restaurant, D is a restaurant, and B is a restaurant. Okay, and then I get these recommendations based on the distance my delivery boy would wanna travel. So in this case, it's like direct edges, and that could say they're directed direct edges. But then the route my delivery boy would have to take is something different, and the time of course would be gone there too, and they would not maybe maybe respect the 30-minute delivery. So this is where directed and weighted graph comes into picture. So they check where's the user's location, where's the restaurant of their choice, of the user's choice, and what's the food preparation time. So food preparation time plus the time taken by the delivery boy would give better suggestions to the users, which could be the quickest one to deliver the food. Hopefully this explains it. Let me check the questions. Tree is also a graph. Cycle is different from self loop. Okay. So in this case, it was like A to A. But then when you talk about loops in general, it's about cyclic property of a graph, which is what I meant. Like, yeah, that's exactly what it is. Cycle has different multiple nodes. So like in this case, it was just A looping with itself, but then there would be very rare cases where you would want to just keep on looping on the same node for solving a problem, but rather loop in a lot of nodes, and and that could be cyclic. So that's what I meant. Tree is also a graph. I would say certain types of graphs are trees. Yes. If so if we in this case make C as the root node, cut off the edges between the siblings, because siblings do not have direct edges, like E and D do not have, say, and A is connected to C, and say B is either connected to A or D, then yeah. So that's ideally in typical world also a graph, and also a tree. Yeah, why not? So hopefully that answers your question. Right. So let's move on to the next slide. So this is time complexities. So this is like different data structures with the time complexities. Like Hosanna was like kind enough to explain us time complexities last time, and we always consider worst case scenarios, which is like O notation, big O notation, and not the theta notation. I just do have it for reference, but then when you actually make a decision on the kind of operations or problem to solve, then you would always go for big O notation. So this is more of like reference or cheat sheet. You can just go through it. It's very simple based on the demos that we saw, insertions, deletions, and search. You can actually correlate with them. Apart from that, like I told you, graphs, we never like gauge what's the insertion time, what's the search time, or what is the deletion time. So that's the reason we don't have time complexities for that. But then other than that, because they are like meant for like solving some other problems. Yeah, so this is like you would get the slide, of course, so you can just refer this as a cheat sheet. Yeah, I do have some questions, I guess. Can you touch on DFS, PFS, and graph? Yeah, so again has answered that. Right. Okay. So this was all about the data structures and the time complexities. If you have any questions, we can of course talk about them, but this is like a cheat sheet and this like applies to all. Right. So I do have a hands-on coding session now, a quick one. So the problem statement, before that, like Yashasvi, do we have time for that?
For practice?
Mm-hmm.
Yes, I would suggest you take the practice, as much as possible here, because we need to have the quiz also, and take
Okay.
questions on Slack later. I am writing that to all our participants that we can continue the discussion on Slack.
Sure. Yeah. Okay. Okay. So let me quickly let me explain you the problem statement. So the problem statement we're gonna solve is about having a playlist, audio playlist. And when I say audio playlist, what is the data structure that comes to your mind? Like if like somebody of you can quickly touch base on that. If I want to implement an audio playlist, okay, W is definitely one. Yes. To make it like fine grain, now I'm becoming choosy. So I want to just move forward. I don't want to come back. I don't want to come back. Yeah, singly is right. Yeah. So let's start implementing that as part of this. Okay. So now, like to visualize it, my audio song is my node, and we would want to make a linked list out of that. So let's implement a quick one. So I would say playlist.
Vijay, your screen shows practice time. Is that what you want to display?
Oh no, sorry. I'm sorry. Good that you told me. Let me share my screen again. Yeah. Can you see my IntelliJ now?
Yes.
Oh, good. Yeah. So for the sake of simplicity, what I've done is like I've already created a class of audio song, which is a node. So one song would link to the next and subsequent ones. So we'll quickly create one playlist. Okay. Yeah. Now my playlist would be having a head node, right? So what I'll do is audio song head. Okay. And this initially is null. So we'll start operation by operation. If we talk about adding a song to a playlist, so we would want to have add operation on my playlist. So yeah, sorry. So my audio song has a song name and a next reference. So when I want to add a new song, so I will pass in a name of the song. Yeah, and this is void, right? And outcome of this would be like, it should be added somewhere in the list. So what I'll do is I'll check if it is null. That means my new song should be the head. So what I'll do is head equals to new audio song with the song name, right? Yeah. So now my head node is having a song. And there could be another scenario that my linked list is already initialized, and I already have like 2-3 songs added to it. So what I would want to do is like traverse through each of the nodes and add it to the end. So let me just do that. So what I'm going to do is while so I'll capture a current pointer or something, and I'll point it to head initially. So this is audio song, right? So what I'll do is while not equals to null. So basically my end node would be always null because it's a singly linked list, right? So what I'm going to do is if it's not equals to null, so I'm going to just traverse through it, and the moment it is to current pointer dot get next. Yeah, so this is like it will start off with head, then move on to the next node because we are assigning next. Then it will check whether my current pointer is now pointing to null. If not, then it will like keep on moving until you actually encounter the last one, right? So when you actually encounter the last one is when you actually come out of the while loop. So at that point, I would want to do dot set. Okay, I would want to create one first. So audio song, and so I would say current pointer dot set next, and I'm gonna point it to the song. Yeah, that's how it should be. This is sonar linked thing that I'm getting, right? So that's what add is. Just keep on adding to the end, like try find and like add it to the end. So this okay, we'll solve this warning later on. So in some cases it could be null pointer is what it's saying, because current pointer could be null or something like that, but we'll solve that later on. So let's see, and we'll just implement a method wherein I say get me a playlist. So I'll just, so not void, so I'll say list of, so list is an inbuilt type in Java. So I'll just print out the names of the songs. So what I'm gonna do is list of say string. I don't want to give out the whole structure out, so that's the reason I'm just collecting the names into a list and then passing on that. So string songs equals to new array list, say. Okay. And I will, so I'm gonna copy this frankly, and like with good coding practices, I would ideally like just like privatize the method and just traverse it. But then with the best interest of time, I'll just copy that. So I'm pointing this, and what I'm gonna do is for every song that I get, songs.add is the song that I get. So current pointer dot get, yeah, get data. Yeah, that's mostly it. And remember the last node would be left off if we just do while. So current pointer dot get data. So basically I'm gonna add this in the end again. So this would be my end node, right? And in the end, I'm going to return songs. So let's quickly test this code by our main method. Say play, like test or something like that. Play or something like that. Yeah. Okay. So what I'm going to do is, so first of all, I'm going to initialize a playlist. Playlist equals to new playlist. Playlist dot add. I'm going to add a song, say Tada something. Then I'm going to add la la. And then what I'm going to do is I'm just going to get the songs. So this is the songs, and I want to print the songs dot which that's what I'm gonna do. I'm gonna print out each of the songs. Let's see if it works out. This is a suggestion. Yeah. Let's see what happens. Okay, I got a null pointer, which is not great. So what I'm doing is I'm pointing to head. Then I'm going to traverse it till it's null. Okay, let's debug this. Yeah, so the first time I got tada, what happens? So if I do this, yeah, so it gets added to my head. Yeah, so the next time I come here, my head is already initialized to tada, and the next is null. Okay. Okay, and now I go here, it should come here. F9. Yeah, so it came here. My head is pointing to this. Should come here. It says is not equals to null. Okay, which is null. So it will, okay, it will directly come outside. Yeah. Okay, it's not equals to null. Current pointer is, okay, sorry, I got it. Dot next should be this. Yeah, and let's run this now quickly. No luck. So debug head gets attached. Now it comes here. So I'm doing current pointer dot get next is not null. So I came here. I created a new song, and what I'm setting is I'm setting current. Okay, so I created a new song. Yeah, and my current pointer dot set next should be the song, right? So this worked. So I think it failed in get maybe. Yeah, it failed in get. Okay, let me do this. Okay, let's run this. Oh, okay, it is printing all the songs in the sequence. So we can ideally like remove and all also. But then with interest of time, I think I'll just keep it, or I do have a code ready for this, which I'll like push out to GitHub and like share the link as well, if that's okay. Gil, do you wanna take it over?
Hi,
Yeah,
Vijayalaxmi.
it's okay, Vijayalaxmi.
Sorry?
We start with a quiz.
Yeah, okay.
Yeah.
So just a minute, I'm just opening the link that you latest, like, can you ping me the link again? Okay, if you don't mind.
Sure thing.
So I can see some comments like, null equals to head would be better practice and all. Yeah, that's true. I mean, this is not defensive. Whatever code we had written is not defensive at all, frankly. But it was just for the demo purpose. And again, like not using Java 8 constraints, which could be like you make it optional and all, which is pretty safe because with the benefit for the wider audience. Right. You guys can see which screen of mine?
Code intelligent.
Okay, I'll share my Chrome again. Yeah. Can you see the quiz?
Yeah, it's quiz now.
Yeah.
So I'd like for everyone to click on the link which I've shared for to share your responses. So our first question, let me activate this question and looking forward to your responses. We'll give it a minute or so to let people access the link and reply. So far, we have got a couple of responses. So what's the best data structure over here? I'm going to activate the next one. Um, I hope all of you are able to access the quiz. I'm going to activate the next one now. Can anyone just reply on chat to tell us if you are having any difficulty in posting your reply before I move on to the next one? Vijayalaxmi, you're the pro, so I didn't give you a link where you can reply. All you have is to show the current question over here. So,
Sure thing.
and Aparna, there's a couple of no's. So, I'd just like to know if you have any difficulty, do post it on the link. I'm getting ready to activate the next question. So it's loading. What would complement round robin? Do we know what's round robin? So visualize a game where everybody gets a turn, fair and square. So if you should have been able to have your screen relaunch. Vijayalaxmi, can you confirm you didn't really press refresh, right? No need for you to do that. Hang on a bit. Did it work? Did it automatically reload? Let's see how many folks have answered. We've got quite a few answers in, so I'm going to activate the next one. Let's see whether your screen should automatically load without you having to refresh. Now I have loaded the next question. A lift with dual door simulation. Okay, I see a few chat where people are saying they cannot see the first question, in which case I would ask you to explicitly refresh your screen. tried refreshing. So, because okay, then not everyone is facing this problem. We have quite a few participants who are able to see the same screen as Vijayalaxmi. As you notice, she didn't really refresh her screen, it automatically refreshed. The login is not required, but feel free to do that. It would help us when we are assessing the responses. Thanks, Shreya. Um, Let me check the replies to this one. We have quite a few, so I will lock it and go in for our next question. So the next question, which should activate on your screen, Dr. Strange had 1 in 14 million chances of defeating Thanos. Sounds like some gaming over here, a gaming strategy. Lots of possibilities. And which one would you choose to win your game? Quite a few people answering. Everybody seems inclined to just one answer. I don't see a lot of um, all right. I think a lot of people are inclined towards tree and graph. Let me quickly check the replies. Great. So yeah, I will post this link again. Sure. Thanks, Yashasvi. So right, Vijayalaxmi, would you like to tell them why which data structure would be the good choice for Dr. Strange here?
Sure. Like as per me, I would say a tree, because with the kind of backtracking history that you keep in tree, you actually can go backwards and just revisit a different answer with not changing a lot of elements to it. So I would go with a tree. Backtracking and keeping a history with graph is also possible, but then it's extra efforts, which tree like by default gives us. And yeah, of course, a special part of graph is still a tree. uh,
Sorry, we had a little bit of a hiccup over there with getting the link right, but I hope everyone is on board now. Let us quickly touch base on the previous answers as well to just quickly see if you had a problem with accessing it before, whether everyone is able to, did everybody reply to this? Did we have any questions over here on this one? Which one did, I think most of the people answered correctly. It happens to be a double-ended queue deck. Is that right, Vijayalakshmi?
yeah, bang on.
And the reason is you would want as compared. So trying each one out. What's a try? Okay, we are going to cover that in a separate session for trees for folks who are interested in more advanced data structures.
Yeah, in this situation, like because you just your person can exit from the front, as well as like the end person in the queue can exit from the rear too at the same time. Yeah, so that's the reason it's TQ. Add
Great.
or insert at the same time. Yeah.
So here, everybody got it right. So I guess I won't touch base much on it. The first one, again, a lot of people did get this right. There were hardly one or two which mentioned a balance tree I gotten as an answer. No, why would I need a balance tree to go through this? I just have a simple requirement, two-way movement. So I guess a balance tree is more when I have efficient looking up in a huge data set. Versus here, all I've got is a simple requirement of going through the video either direction, either backward or forward. So that touches base on a few questions that we have had so far, whether while people had a few problems with the quiz. Now going on to our next question. I hope everybody is on board with the quiz. Try your luck with this one. Which data structure would you choose? I think mostly I'm giving everyone a couple of minutes. So far, everyone looks like they've done a good job. More answers, more responses, please. Can everyone's, I hope everyone is tuned into the same question which is displayed on Vijayalaxmi's screen. Great. Thanks, Anu. And I think everyone has given the right answer. So good job. I think everyone has really taken away the point which Vijayalaxmi made during the really insightful session. How about the next question? A weekly timetable for my 10 standard CBSE class. What data structure would I use? Quite a few correct answers. Great. Looking forward to have more answers in. The audience is really great. We've got everybody giving in the correct answer over here. The next question, again, Vijayalaxmi touched base on it during this session. Do we recall what she gave us for a good data structure for this one? Responses are pouring in, and again, great. It's really cool that everyone's agreed on this data structure as well. Let me lock it and get ready for our next question. Great. The answers pour in much faster than the picture does on our slide, but we've got a great understanding here too. Really looks good with everyone's answers. So we're not partial. So somebody who answered stack, this is an impartial restaurant. You take your turn as you come in, you get admittance into the restaurant. Somebody mentioned first in, last in, first out. Boy, that would make a lot of customers unhappy. Activating the next question. And what do we have here? Each carton in a bigger container of may satisfy one of these quality checkpoints. So I have to run this check for 27 items. Somebody says binary tree. Well, binary tree is when I am got two options for each, and I would have further processing. So not really. So a lot of folks have given linked list. So the key to take away is the numbers are fixed here. I have 4 outputs: excellent, good, average, and poor. And I've got this quality check to be carried out for 27 list items, which happen to be milk cartons. So, well, a linked list may do, but not required when I have fixed items in question. So most people have answered correctly. It is an array. All right, thank you so much. I hope all of us have taken away a thing or two from our quiz today. And what's next on our agenda is for the practice problems posted in the data structures channel. I hope a lot of folks will take a look at it and keep posting your queries and feedback and attempts on the practice problem. Do join the Slack channel.
Gail, before signing off, like I just wanted to make a point. So hopefully I have made what your 2 hours. If so, just let me know as well. That'd be great.
Yes, thank you, Vijayalaxmi, for the wonderful session. It was very nice, and we learned a lot. And I would request all participants to join the Slack channel and continue discussion over there, and provide us feedback, provide us suggestions to what to include or any topics particularly folks are interested in. We can definitely cover in our upcoming sessions. So thanks again, everyone. And please do continue the discussion over the Slack. I have posted the Slack links. Hope you all will join. And Gail, also post the quiz answers on the channel. That will help.
Good thing, Yashasvi.
Yeah. Thank you. Thank you, Vijayalaxmi. Thank you, Gail. Thanks, everyone.
Thanks. Bye-bye.
Bye.